Hi, my name is Andres Nam, and this is a shorter, deeper dive into power analysis for hypothesis testing. And it's a continuation of the videos I've done on power analysis introduction in general, power analysis on confidence intervals, and now this is the third video. So, a slight introduction to this deeper dive. So, let's reiterate the definition of power analysis for hypothesis testing. Our aim in this case is to determine a size for the sample to reject null hypothesis with a certain probability called power if the null hypothesis is false. To be able to do this, we need certain input data to be able to determine what sample size we need to reject null hypothesis with a certain probability. Because what occurs in practice quite often is that although null hypothesis is false, we might not be able to detect it or detect the significant difference because the interval that we generate for the null hypothesis is too wide compared to the difference that we have for the alternative hypothesis. And I will talk a little bit more about that. But let's start with the input variables to determine the sample size n. So first of all, we need something called the effect size. And I will do a deeper dive on this as well. But essentially, it's the difference we want to be able to classify as significant with a probability called power. What you need to know about this is that the larger the effect size, the easier it is to detect this null hypothesis being false, to detect the significant difference. And the smaller the effect, the harder it is to detect the significant difference. We also need, as an input variable, the standard deviation of data. We, of course, need the test confidence, 95% or 99% confidence. So basically, this is the probability of avoiding type 1 error. So basically, rejecting null hypothesis, assuming that actually null hypothesis is true. And we need to set the specific power. So basically, this is usually set as 80% or 90%, but it's the probability of rejecting null hypothesis, assuming that it is false. Or it can be said as well that its power is the probability of rejecting or avoiding type 2 error. And type 2 error is the probability of not rejecting null hypothesis, assuming that null hypothesis is false. And now I'll talk a little bit about effect size. So here in this slide, I have brought in the formula for effect size, which is this. So it is the difference between two means, the mean based on the null hypothesis and the new mean that we have received usually from our new sample. And we divide that difference between the means with the standard deviation of the data. And based on that, we can get the effect size. So here there are two examples. One, an example about small effect, and another example about large effect. As you can see, in one case, the difference between the means is very small, and the standard deviation for both of the means is quite large. So naturally, the effect size, or this variable here, is quite small because the difference is small, but the standard deviation is big. So the division actually makes it smaller, the effect size. And here is another case where we have a large effect where the difference between to-do means is quite large, and the standard deviation for both data sets is very small. So as you can imagine, because the difference is big, and we divide the difference with standard deviation, which we are assuming is the same for both data sets in this case, and it is small, then we will have quite a large E value. And essentially what we are trying to say with the effect size is if we are assuming that the difference between alternative and null hypothesis is going to be big, if it exists, we can actually, we don't need as much data to actually prove this difference. But of course, in another case where the difference that we want to see is very small, assuming also the considering also the standard deviations, then we actually need quite a lot of data to find this significant difference. And I've written a tiny tutorial here as well on this topic. It's just an introduction to power analysis and this effect size. But the effect size, you can think of this as what size effect in regards to the standard deviations of the data you would like to be able to detect with a set power. And again, this is the formula for this effect size. And it's important to understand this effect size is something that we set for the experiment beforehand, because it's actually not possible to set it afterwards because we need this effect size to calculate the sample size. So it's usually based on some previous literature review or actually just some kind of classification or where we want to understand what difference we want to detect. We don't want to be able to detect like a randomly small experiment effect. We want to be able to detect quite some meaningful effect, and that comes from actually just understanding the data. This is not the same for different experiments, or it's not basically mathematically derivable. And just a little bit of a deeper dive into this effect as well is that actually, if we look at this this chart over here, if the effect value is larger than 0.5, we can say that there is quite a large difference for the effect. And this is derived by actually this scientist called Cohen, who, okay, and here, and as also like this effect is something that can be, for different scientists and for different people, it's a little bit of a subjective value. But here this Cohen, actually, he also brought out that there is for effect values that we calculate, there is like a classification of small effect, medium effect, and large effect. So here it said that actually effect above 0.8 is considered as large. And this effect actually itself can be translated into something very interesting, something called the percent of overlap, non-overlap between two distributions. So you can think of this as if you have two distributions as shown here. Here the percentage of non-overlap is actually 100, but here the percentage of non-overlap is much smaller. And the larger defect you have, the larger the percentage of non-overlap you will have. So this effect side is something that it needs time to understand it well, but it's very important.